Chapter 9 in your book starts dealing with the concept of statics and introduces a new concept called torque into our vernacular. So what is statics? Statics is incredibly important in engineering. Statics is the study of the forces in equilibrium, that is, the forces balancing. So if forces balance, then there is no net force. If there is no net force, there's no acceleration. So statics is basically the study of objects that follow Newton's second law, where the net force is equal to 0. So this is the key equation for statics. Now it makes it look really simple, right? Oh, one equation, that's easy. It actually can be pretty complex. In building bridges, for instance, you want the bridge to be static. You don't want your bridge to accelerate. That's a very bad thing if your bridge is falling. So you have to come up with all of the forces on all of the girders, all of the arms, all of the, for a suspension bridge, all of the cables. So the net force will end up being 0. For buildings, again, you don't want your building to accelerate. That's a bad thing. So you have to come up with engineering to make sure your building doesn't accelerate. So all of the forces acting on an object are 0. Picking what materials are needed, where to put your supports and things like that is incredibly important when dealing with building bridges and building buildings. And statics actually has an entire semester of engineering dedicated just to studying this phenomenon. Now, just because there's no acceleration, because if the net force is equal to 0, the acceleration must be equal to 0, doesn't mean the object has to be stationary, right? Now, of course, bridges are stationary. Buildings are stationary. But statics only worries about the acceleration being 0, so the velocity can actually be moving. So static equilibrium deals with the net force equal to 0 and the velocity equal to 0. But you can have a situation where you have a dynamic equilibrium. Again, equilibrium where all the forces add up to 0. Dynamic equilibrium means that, again, all the forces add up to 0, but the velocity is not 0. Those are fewer cases. We're going to mainly look at this static equilibrium problem. But just because the forces on an object are 0 doesn't mean that object necessarily isn't going to move. So we need to introduce and talk about the concept of torque. Let's look at an example of an object that can rotate. For example, a merry-go-round. So we're going to look at a merry-go-round from above. Now, if we're looking at it from above, of course, the weight of the merry-go-round is going into the board, and then the normal force from the surface is coming out of the board. Those two forces balance. So the forces, what we would think of as the y direction if we're looking at it from the side, the forces of the weight and the normal force balance, which means that the merry-go-round is in equilibrium in that dimension. But looking at it from above, I can apply 2 additional forces. Imagine I have 2 people pushing on the merry-go-round. Depending on where they push, you can get dramatically different results. For example, here on the left, I have someone placed on one end pushing into the merry-go-round through the middle, through the rotation axis. I have someone else over here pushing on the merry-go-round. Now imagine the merry-go-round isn't fixed on a pier. Imagine it has big wheels on the bottom. Well, in this case, the merry-go-round would not move. It would not rotate, but neither would it slide back and forth or up and down, because these forces are equal and opposite on the merry-go-round. They balance. The net force for this example is 0. If the force is 0, there is no acceleration. This is our equilibrium criteria. But look on the right. I have the same 2 people pushing with the same 2 forces in the same 2 directions. I just apply the force at a different point. Here, this person pushing to the left is now on the edge of the merry-go-round pushing to the left. This person that was pushing to the right is now at the top of the merry-go-round, from our perspective here, pushing to the right. Again, even if this merry-go-round were on wheels, it has a rotation axis, but the whole merry-go-round can slide around. this merry-go-round would not move linearly. It would not slide to the right or to the left because the force is balanced. The net force on this object is equal to 0, just like it is over here. However, I think we can all agree that this is not going to be a stationary merry-go-round. It's going to start to rotate. Right? That's how you spin a merry-go-round. You don't push into the middle or pull on the merry-go-round. You stand on the side and you give it a sideways force. Here we're standing up here and we're giving it a sideways force. Here we're standing at the bottom, giving it a sideways force. That causes the merry-go-round to rotate. And a rotating merry-go-round is not one in static equilibrium. So the fact that the net forces are 0 in both cases, and one of these cases causes the merry-go-round to move, the other one, or rotate at least, and this one doesn't, means that just having the net force equal to 0 is not a sufficient criteria for equilibrium. We have to talk about what's going on over here on the merry-go-round on the right.